Okay, hello everybody. So we're gonna look at examples of functions that have any input space, but always output just one real number. So the derivative will have the same input and output space, so the input will be the same, the output will be the same, because the derivative here is a map, it's a linear map that approximates this map. Completely different is a map that goes to a different output space, namely back to the input space. And this kind of a map, any map that does this, is called a vector field. Now in this case, we are building this vector field in a very specific way. We're building it from the function f. We're creating a vector field, and that vector field is called the gradient of f. Okay, and it's written as an upside down triangle. You could also call this grad f. Let's see examples. Here's a function. It has one real number output, and that means we can create the gradient. But let's first do the derivative. So the derivative of f at, let's say at the point P, or really just at the point xy. Well, that should map R2 to R. It should have the same output space as the original map. And so we have to invent some names, some new names for R2 because we still need x and y. And we'll send it to, well, v1 times the first column of the Jacobian plus v2 times the second column of the Jacobian. So remember here, the Jacobian has two columns, one row. So it just looks like 2x, and then the second column is 2y. And now, what does the gradient do? The gradient says, let's create a new map from from the input space back to the input space again. And let's take the point xy and send it to the vector, which is just that row. It's just the row of the Jacobian, but it now interpreted as a vector. So we are just interpreting. So interpret this differently. So the derivative took this and made a linear combination of its columns. Here's a linear combination of its columns. And the gradient says, let's make a map, a completely new map. Okay. Anyway. Okay, so that's our first example. And now, I just want to show you something here that's sort of interesting and will be extremely useful. So let's look at this and realize that we could think of V is a vector. It's a vector in R2. And we could take its dot product. Its dot product with what? With the gradient at the point xy. And so actually secretly the whole time, the derivative, this is a dot product, is a dot product when f maps to the real numbers. So in the case where your function has output a real number, then actually the derivative ends up being a dot product. Otherwise, you have another thing here, and then, it's not clear how to make this into a vector. It has too many numbers to be a dot product. Like if this was R2, then there'd be another thing down here, and the Jacobian matrix would look like that, and it'd just be there's too much, so it's not a dot product really. But here, when our output is R, then actually the derivative can be seen as a dot product. Okay, and we can write this like, we could write this as v dot product with the gradient of f at the point xy. This is the gradient of f. Gradient of f evaluated at the point xy is what we get when we plug in, namely this vector. We could also obviously write it like this with a comma. It's the same vector. Another example. Let's do this example. Okay, so here let's just do the Jacobian first. Jacobian has 2x. The second column is 2y. Third column is 2z. This was partial x. This was partial y. This was partial z. You could even write this as partial of f with respect to these. It's whatever you want to write. And again, it has one row because the output is one-dimensional space. So that means we can create the gradient. Now the gradient will be from the input space back to the input space again. And it takes a point. Where does it send it? Well, it sends it to exactly that one row of the Jacobian. Okay. And let's take the derivative. The derivative would look like, well, the derivative at a point. So let's say at the point x, y, z. It has to be a map from the same input and output. So that's why the derivative is not the gradient. The derivative is not a vector field. It's just, and because we have to do it at a point, we have to pick a point first in order to linearize at that point. Well, we need to come up with some new names. In fact, I can write them vertically here. v1, v2, v3. So that's a new input vector. And where does it go? It goes to v1 times 2x plus v2. It's just a linear combination of the columns of the Jacobian matrix. Now in this case, the columns are just one number. So again, we're going to have something special here. Whenever our function has one number as the output, then this is a dot product. This is a dot product. It is the dot product of v with the gradient of f evaluated at that point. This is a vector, right? It's that vector. And this is a dot product. So actually, the derivative of f at the point x, y, z in the direction v is equal to the dot product of v with the gradient plugged in at that point. So, I mean, we can obviously write a dot product in many different symbols. I'll just remind you of another symbol. And just to be clear, like this, when we plug in at a point, will be an actual vector. So like at the point 2, 1, 0, this becomes the vector 4, 2, 0. And so this would be a dot product of our movement. We can move in any direction and take its dot product with 4, 2, 0. Okay? And that would just be, v1 times 4 plus v2. We can take any movement step, move in any direction, and just take the dot product with the gradient. Okay. Let's do another example. Here, this example, let's look at the Jacobian matrix. Jacobian matrix. Well, now I have to take the derivative with respect to x. So what am I going to get? 3x squared over 8 plus a 2y. Derivative with respect to x gives me 2y. Derivative with respect to x is minus 2. That's just minus y squared. Okay. That's just one number. It's the first column of this Jacobian. that has one row and two columns. What's the second column? Well, the second column is partial y. So we can do that. 0, 2x, and then partial y is minus 2xy, and then a 0. Okay, and so from that Jacobian, we can create the gradient vector field, which now maps the input space back to itself. And so how does it do that? Well, it takes a point xy to, well, this thing. Comma. So I'm just reinterpreting. I'm just taking these partial derivatives and putting them as the components functions of a new map with a totally different output space, namely back to the input space. The map doesn't go to R anymore, it goes back to R2, and that is the gradient map. It goes back to R2. Contrast this with the derivative of f at the point xy, which is a map from R2 to R, because it has to be. It has to approximate the original map. And now we need to come up with new names, because we had to take the derivative at a point. So we have now a movement vector, new names for these variables, these input variables. And we say, okay, well, v1 times this number plus v2 times this number, where they're exactly these two things again, right? And this is a linear combination of columns of the Jacobian, but since the Jacobian columns have just one entry in each of the two columns, then this is actually equal to a dot product. It's equal to a dot product in the special case where the output of our function is just a real number. And what is its dot product? Well, it's the dot product of v dotted with the gradient of f evaluated at that point. It's dot product of this. Amazing coincidence. Okay. This is the reason why the gradient vector field will be. So look down here. All these gradient vectors are going to be orthogonal 90 degrees with respect to the contour lines, and we will see that in the next video. Look over here. Again, they're all 90 degrees with respect to the contour line. This is all the values of 0 that took 0 in the contour. Level set. And the reason is because of this dot product. Remember that it'll be the length. The dot product is equal to the length of the first vector times the length of the second vector. This is just a vector. It just takes a lot of things to write because we didn't evaluate it and get an actual vector yet, times the cosine of the angle between. And this cosine is going to give this 90-degree angle between the gradient and the contour. Okay, we'll see that in another video. So, excellent. We saw several examples of the Jacobian. We saw that there's now the derivative becomes a dot product with the gradient. The derivative now becomes a dot product with the gradient. The gradient, though, is a vector field. It has a completely different output space. And so the derivative and the gradient are very different, but they are related because in this case, where the output space of the original function f is a real number, then the derivative in direction v is just taking a dot product of v with the gradient at that point. So we'll see this in another video.